Diffusion and Effusion. We will now move on to talk about effusion and diffusion. We'll very quickly speak of the difference and then focus our discussion on effusion. Diffusion occurs when there are two gases that are mixing relatively freely. For instance, let's say that I spray some perfume on one side of the room and then I spray enough of it. Eventually, the people on the other side of the room will smell it. The perfume mixes with the molecules that are making up the air. Effusion is a bit more complicated, and honestly, the definition gets a little muddied. The actual definition, as generally stated, is that the molecules go through a very small hole, or holes, into a vacuum. That being said, often if things are going to go through small holes into other gases, it will often get labeled as effusion. For instance, a helium balloon that's leaking helium through the pores of the rubber will often be considered effusion, even though technically it is mixing into the air, and it is technically diffusion. So just be aware of the differences here. Though on any exam, I wouldn't give you any sort of muddled definitions. It would be gas going through a small opening into a vacuum equals effusion. Now let's talk about one specific use of effusion for isotopic enrichment. In chemistry, isotopes, or atoms with the same number of protons and electrons, but a different number of neutrons, can be very difficult to separate. They can't be separated out chemically, but they have to be separated based somehow on mass. And there's a few ways of doing this, but one of them takes advantage of effusion. If you can turn an element into a gas in some form, the lighter the gas, here represented by being smaller just so that it's visual, though of course in reality they're the same size. But the smaller gas will go through the semi-permeable membrane at a much higher rate. You can then collect those samples and send them through many phases of this. And each phase you're going to get closer and closer and closer to a pure version of the isotopes. This is actually one of the ways that we can enrich uranium, for nuclear weapons and for power. We can't simply dig uranium up from the ground and use it, because only one isotope of the uranium is actually any good for radioactive systems. And that isotope is only about 0.7205% abundant, and so we have to separate those out. There's a lot of ways to do this, but one of them is through the effusion that we talked about in the last slide. Since uranium-238 is going to effuse slower than uranium-235, if we can actually turn this into uranium hexafluoride, it's a gas, and we can use the difference in mass to separate the isotopes out by effusion. And this takes many, many, many thousands of stages to be able to actually get this to the right purity to be able to do this. And so here I have one of these facilities pictured. It's 4,000 stages. It's a half-mile long and 6 stories high. And that's in Tennessee. Again, there are other ways of separating this out. This is just one of them. Now, let's set up a quick and useful ratio that we can use in many different calculations. Now, I want you to note here that the process is important too. This isn't a derivation where you want to skip over the process and just use the final result, because you'll need this process in one other place in this video even, and some other places in your homework. It's also something that we do very commonly in chemistry. Let's start with the equation for URMS. We have the root mean squared speed. From here, we're going to solve each one for temperature. Why are we doing this? Well, both gases are at the same temperature. So if we do this, we can say that the two different gases are at the same temperature, then we can set the equations equal to each other. So for two different species at the same temperature, we have this. Notice it's the same as the above equation. We've just changed it into the mass A and mass B. Now, we also know from here that we can cancel out the 3 and the R since those are constants. Once we do that, we can rearrange a little bit to put our UR masses on one side and our masses on the other. And when we do this, we get a ratio of the rates to the masses. So for our final result, we have R1 over R2 equals M2 over M1. Now, a quick take-home project for you. I want you to do the exact same thing that we just did, but this time, do it for the time that it takes to effuse rather than the rate. Remember that time isn't in this equation, so you need to make one logic step on your own. You're welcome to work from the final ratio on the previous slide as well if it helps. In review, diffusion is when a gas spreads into another gas. Effusion is when a gas goes through a small hole, or several holes, as in the case of a membrane, into a vacuum. As the mass increases, the rate of effusion decreases. And this makes sense with what we have based on the UR math speed. In the next video, we'll be doing lots and lots of examples.